So for today, sensors. All right, so back to this slide from the beginning of the semester, we talked about a mechatronic system that we have some existing state, the environment we're trying to learn about. Maybe we're trying to influence the environment. We use sensors to detect what's going on. We send that information to our controller, which analyzes that information, maybe incorporates it with other information we have, and makes the decision to do something. If it decides to do something, it sends a command to some actor, usually an actuator of some kind, to make a change, to change something. And then we check and see, did we achieve the desired state? If not, then we go through the loop again and we continue to change. So we're going to implement this in the lab. You're going to play with a bunch of different sensors. And in the final project, you're going to create a system that does this, that uses sensors to figure out what's going on and command the robot to do what it needs to do to achieve the desired state. So let's just talk for a minute about sensors, what they are, and what do they do. So obviously we have that the sensors collect information about the environment. And they do that by using various physical principles. So this is really where physics and chemistry coincide with engineering. We're going to delve briefly into the world of physics to see, what do we know about what are various physical properties that exist in the world, and how can we exploit those to learn about the environment? And that's what that handout deals with, which I referred to earlier. And we'll talk about that more in a second. So let's just brainstorm for a minute some various sensor types. What are things we might sense, we can sense?
Like using a photoresistor to sense light.
Okay, we can sense light. Very good. And a photoresistor is one way to do it. There's also phototransducers and photodiodes. What else?
You could also have a pressure sensor and accelerometer.
Yeah, pressure, acceleration. Very good. Pressure is maybe another word for force. They're not. It depends. Let's make that its own one. What else?
Sound.
Sound. Very good. Okay, so maybe that's the same as vibration. Maybe it's not.
You could be sensing your own signal, like using a diode with the, I think it was the photodiode, and then seeing like whether that signal is being blocked or not. Okay, so you're describing the way in which we sense something using an encoder. We'll talk about encoders here in a second. What would you use an encoder to measure? What physical property are you trying to measure? Like angular velocity, I think, is one of them. Okay, so let's just say speed. Yeah, angular velocity. You could also have linear velocity with an encoder. You can have a linear encoder. What are the various sensors in your car dashboard?
Distance traveled.
Temperature.
Distance traveled. Okay, so position maybe. Yeah, that's called an odometer, right? With the robotic stuff I do, we call it visual odometry. using a computer to track how we've moved, what our position is relative to where we started. In addition, they call it visual odometry because they're specifying it's in contrast to wheel odometry. So what your car does is wheel odometry. You have a wheel that's in contact with the ground, and we keep track of how much it turns, how many times it rotates, and we can extrapolate how far the car has traveled. With a flying vehicle, you don't have anything in contact with the ground, so you can't do a physical odometry in that way. So we use cameras to do visual odometry. Okay, so you said someone else. So Matt said odometry. Said odometer, and that's a position sensor. What else, or a distance?
Temperature.
Yeah, temperature. Very good. You've got a speedometer in there. You've got.
Would you count a GPS as a sensor?
Absolutely. And so what are you measuring? Well, you're measuring position. You also measure altitude, which is really just a form of position. But you can also measure, so you can measure altitude GPS. In the olden days, we measured altitude with a barometer using, which measured barometric pressure. So that's a different way to measure altitude. And still, modern sensors still use barometers. The flight controller we're using on our new quadrotors has a barometer built in to measure altitude.
Sir, can you measure orientation with like a gyroscope?
Yeah, right. Great. So attitude, very good. Or orientation, I like that. Hey, I started off class with an example, and in that example, they're measuring strain or deformation. Those are good mechanical engineering things. We can also measure like magnetic field, radiation, etc. And we could go on and on. All right, so let's proceed here. So to summarize, sensors collect information about the environment, and they take a measurement and convert it to a usable signal. What is the usable signal?
Ultimately, a voltage.
Okay. Good. Typically, it is a voltage. So, what can we're gonna take our sensors and connect them to our microcontrollers, or we might connect them to a computer or something like that. And what can our microcontroller read? What are the available inputs?
An analog or a digital input.
Analog or digital what? Adam said it. So
Voltage or time?
yeah, voltage or time. Someone did the reading. Good job, Adam. Our microcontroller we like to think of it as measuring voltage, right? We can make those pins, we can declare our pins as an input, and then it can measure the voltage either digitally or analog, right? So most sophisticated microcontrollers have an A to D converter built in, which is what we have. And so the voltage can be analog or digital. How do we measure time with our microcontroller?
Charging and discharging of a capacitor.
Well, that's the one way we did it in the lab, but we can time from when the time between state changes at a pin. So we used a capacitor circuit to basically ultimately measure the resistance of something, but you could just hook something up to a pin and measure when it goes from high to low, and you can count the amount of time that passes between it going from high to low. So that's how we measure time. So so we can have analog or digital voltage input. Move that out of the way. And a microcontroller. All microcontrollers have timers. They have to in order to make all the computing work, just like what we talked about in the digital logic lessons we just did. Microcontroller timers can measure time between events. And that can be correlated to some physical properties changing. In the RC circuit lab, we use time to measure how the light was changing on our photoresistor. So hopefully you remember that. I'm sure you will never forget. It's painful enough. Okay, so we use various physical principles, which we'll talk about in a moment. And here's some different types of sensors. So this is a robot from a couple years ago, a final project robot. It had some light sensors on it and various other things, magnetic compass, things like that. So we'll talk about a wide variety of sensors you have available for that final project. So here's some of the physical principles. You have, so for example, and this is what's in the handout. Let me show you the handout. There you go. That's what the handout looks like. The reason I'm giving you this handout, I think it's interesting. I like learning about these different things. But you will have a homework assignment, which is to take one of these physical principles that interests you and write me a half-page summary about it. So I'll highlight some of these quickly here on the slide, but for the homework, I want you to do a little research. You can look in the book, or I encourage you to go online. So tell me about the physical principle. Tell me how it works. How it's used for sensing, or how it could be used. A lot of times, most of these principles are being used in sensors, but some of them are a little more obscure, and you may not be able to find an existing sensor that uses this principle. But tell me how it might be used for that, or what you would sense with it. So then I want about a half-page summary and email it to me. In the past, I have manually deconflicted to make sure that no two people do the same physical principle. I'm not going to worry about that so much today because this is complicated enough doing online class. So just don't everybody pick the Coriolis effect, since we know it's all your favorite after having taken dynamics. So read through the list and do something interesting that's interesting to you. Okay. All right. So back to these physical principles. So one such physical principle is the piezoelectric effect, and that is that for certain materials, when you strain them, so you apply a load to them, a charge is generated. And we can use that effect to measure force. We can use it to measure displacement. For those of you in 460, have you done the accelerometer lab yet? The vibrating beam with the accelerometers on it?
We haven't yet, but we discussed how the accelerometer works with the crystal in between.
Yeah, so those are piezoelectric crystal accelerometers. Okay. Photoconductive effect, when light strikes semiconductor materials, the resistance decreases. So that's a phototransducer. We will use those. Those will be used in the encoders that we're going to play with. Piezoresistive effect, resistance is proportional to an applied stress. So that's how a strain gauge works. Faraday's law, we'll talk about a type of sensor that uses a magnetic field. The Seebeck effect is used in thermistors, which is a way to measure temperature. Do you guys use those in any of your thermal fluids courses? Thermistors, measure temperature?
I don't think we've ever used a thermocouple in a class so far that I've seen, but
Okay. And then we all know and love Newton's law, right? So that is used to help us measure acceleration. Okay, so let's talk about some ways in which we characterize sensors. So first of all, we want to jot down this definition of a transfer function. And if you've taken Mech 325, you've heard about a transfer function. And this is the same thing we're talking about here, except that the transfer functions you may see for different sensors may look different than the transfer functions you saw in system dynamics, Mech 325. So the transfer function is the functional relationship between the physical input and electrical output signal. So the physical input we call the measurand, that which is being measured. So that's really important in understanding how a particular sensor works. So there are a number of metrics we use to characterize how well a sensor works, how good it is. Okay, so one that's very common is the sensitivity. So that's defined as the relationship between the input physical signal and output electrical signal. And you're probably thinking to yourself, that sounds a lot like the transfer function. The transfer function is the transfer function might be a formula or a plot or something like that that shows the relationship over a large range of values. The sensitivity is going to be more like a single quantity. So this might be if it were a thermistor, its units might be ohms per degree Celsius, something like units like that. Okay, how much does that electrical signal change for a given change in physical property? As for a strain gauge, it might be ohms per strain, per microstrain, something like that. Okay, so the next one is accuracy, and that is the largest expected error between ideal and actual output signal. Okay, so let's think about what that means. That didn't come up. You're trying to measure something. Ideally, you would measure the actual quantity. So if I'm trying to measure the speed of my car when I'm driving down the freeway, I want it to tell me how fast I'm actually moving. But the sensor, the output signal of the sensor is not going to be the actual speed. There's going to be some error in there. So what is the largest expected error? And if you're looking up, you're comparing different speed sensors, they should report what they expect their error to be, that their error should be within a certain range of values. Okay, dynamic range. Anyone know what dynamic range is?
It's like the range of signals that it can actually pick up.
Great. The range of the measurand it can detect, and I would put in parentheses accurately, because it's not super helpful if it can detect things inaccurately. Although, as long as it's repeatably inaccurate, then we can sometimes compensate for that. Okay, resolution. You hear resolution talked about a lot in what context? When do you hear about resolution?
Photo resolution.
Yeah, photos, cameras, things like that. So resolution is defined as the minimum detectable change in the measurement. So it's, what is that smallest amount of change? So if you have a temperature sensor, and if the temperature changes from 71 degrees to 72 degrees, but the sensor doesn't pick that up, its resolution is not high enough to pick up that 1 degree change. Maybe it only recognizes a change in temperature when the change is 5 degrees. So then its resolution would be 5 degrees. So that's really important if you're trying to detect small changes. So obviously, as everything in engineering, it depends on the application as to what you can get away with. Okay, noise. So that's what is noise? And I'll just tell me what you think noise is, and I'll give you the book definition.
Would that just be like how it handles interference? How sensitive it is to like any interference?
Okay. So how would you know it's an interference? Well, so it's kind of a trick question. You don't necessarily know, and that's the problem, right? So you're just, if your microcontroller has a sensor hooked to it and you're reading a voltage, you're just looking at that voltage. You know, maybe it's a voltage over time. How do you know what you're seeing is the actual change in the environment versus the change in versus what might be noise added to that? So noise is any feature of the output that's not present. Whoops, that didn't come out right. Not present in the measure end. So that's something that's corrupting the signal. So you can think about it as corruption. The problem is if you're just looking at an electrical signal and looking at a voltage, you don't know what's noise and what's not. And so there's lots of people who work very hard to figure out how to deal with noise, how to reduce it, how to compensate for it. Okay, so linearity is usually recorded as its maximum deviation from a linear function. Why is linearity important or desirable?
Because it allows you to create an accurate transfer function.
You can have an accurate transfer function if it's linear or not, but it's definitely simpler. So with linearity, we're talking about, so say you have a temperature sensor, or you want to measure temperature, and the real world temperature is changing like this, so degrees Celsius, and then we're getting some voltage out, or maybe it's a resistance. Is that straight mark? It would be nice if there was this nice linear relationship. And so what that would mean is that if I detect, so say this is 2 volts and this is 3 volts, if my microcontroller tells me that the sensor has reported a 1 volt change, that means that corresponds to the temperature change. Let's say that's 10 and that's 20. And it changed 20 degrees. And then a moment later, I get 4 volts. And so I've changed 1 volt again. That means I added another 10 degrees. So in this case, if we're linear, 1 volt per 10 degrees. Well, in reality, in real life, you're probably going to have something that's more like, maybe it's like this. Okay. And so when you record a 1 volt change, oh, maybe the delta T is only like 3 degrees. Here, But then when you're in this region of the plot, a 1 volt change is much greater. See that? So that's the difference between linear and non-linear. And so we can deal with non-linear sensors, but it's just more complicated. It's a lot simpler to have a linear sensor. What you often get is the manufacturer will tell you the sensor is linear within this range. So then you try to limit your use of the sensor to that range of values. Okay, any questions on that? It's an important concept, something I didn't fully appreciate until I was in grad school. Okay, hysteresis is a funky thing. There's a picture of it over here on the left. Anyone know how hysteresis works or what it is?
It's like the outputs you get as you move up the dynamic range is different than as you move back down the dynamic range.
Okay, great. So that was good definition, I think, of Matt. Change between output. So here's a dictionary way of describing it. A change between an output when approached from below versus above. So it's quite possible you haven't heard of this before, and that's okay if you haven't. There are some things, and it's just the nature of the world, that if you're taking a measurement, say you're measuring temperature and you're boiling a pot of water, and as it heats up, you get a certain measurement. But then and the measurement follows a certain path, maybe something like well, in this case, it would be there's the actual temperature and there's the voltage you're measuring. And then when you're done boiling the water, you let the water cool down, and the voltage output takes a different path on the way down as the water's cooling off than it took when it was heating up. That's known as hysteresis. Obviously, hysteresis is a big pain for certain things because it means you're going to get, even though, at 75 degrees, you might get a different voltage output depending on if you're increasing the temperature or decreasing the temperature. So if that change caused by the hysteresis is significant to whatever you're trying to do, then you need to figure out how to deal with that. Basically, that would mean you need to not just know the temperature at the given time, you need to know the change in the temperature. Has the temperature been rising or lowering, and factor that into your calculation. So hysteresis can be a big hassle. Okay, last one I want to talk about is bandwidth. And if you've taken system dynamics, ME325, you should have talked about bandwidth, but you may not have realized that it applies here. So the bandwidth is the range of frequencies of an input that can be detected. Okay, so what that has to do with is also how fast can you measure something. So, like think about things. Informal poll here. What measures faster, a thermometer or an accelerometer?
Accelerometer.
Yeah, generally from your personal experience, you probably realize that an accelerometer generally measures much faster than a thermometer. Always seems to take a while to register a measurement. So you would say that a thermometer has a much lower bandwidth. than an accelerometer. Okay. So in controls or in like system dynamics, we plot a bandwidth on a transfer function. So you've probably seen something like this where you put frequency down here, omega, and then that might be hertz, or it might be rads per second, something like that. And then we have the output of the magnitude and hj omega. And so this would be a typical looking transfer function for a first order. And that's what you might get for a typical sensor. Something like an accelerometer might have a more a second order system might have a bump here. Okay, so what this is saying is that when frequencies are low, and this is usually 1 here, you want the output to be matched to the input. So when frequencies are low, the output matches the input, meaning that there's a gain of only 1. When frequencies get high, the output, so what's hj omega? You guys remember that? That's output over input. Is this all completely new stuff, or have you seen this before?
It's been a little bit, but I think we
Okay.
have seen it before.
Last spring in system dynamics, I hope. So output over input. You would like the output over input to be 1. For most physical systems, as the frequency of the real life phenomenon starts changing a lot, like to imagine you had temperature rapidly changing, like milliseconds. A typical thermometer, a household thermometer, isn't going to be able to keep up with that. It's not going to track those changes. So its output compared to input is going to drop off. And that's what we see. That's what this means. So most devices, physical devices, can't sense things at high speeds. On the other hand, there are some sensors, accelerometers usually don't work very well at low speeds if it's using an inertial measurement system. Okay. So anyway, that's those typical performance metrics. All right.